So let's, we're going to talk about some quantities of motion today. Okay, quantities of motion. So, the space shuttle. I think has that program been discontinued? No more space shuttles, right? Or do they still do space shuttles? What they all said. Okay. I didn't really understand anything. Everyone was kind of talking at the same time. But we still send people into space, though. So, and then probably someone's going to be on Mars in our lifetime. That's pretty cool. All right. But not on that. Okay, so that's probably a picture from the 80s or the 90s. And so here, this is a table of the velocity of the space shuttle every second after takeoff. That's cool. All right, so here's the set. So 0 seconds, the velocity of the shuttle is 0. At 1 second, 30. At 2, 60, etc. So what do you notice about the velocity? What do you notice about the velocity? Yes, sir? So the velocity is 30 at one point in time, right? Okay. But so just talk about velocity, though. Just talk about velocity. What's going on with the velocity here? Yeah. So yeah, the velocity is increasing by 30 meters per second every second. Do you see that? Okay, so I want you to predict the velocity at 5.7. Any way you can. Any way you can. 5.7 seconds after takeoff, what is the velocity of the shuttle? Do it by yourself. Do it with a partner. Whatever you want. I got my list. So be ready. Okay, where's Pedro? Pedro here? How'd it go? And how did you get that? Tell me what you did. Okay, 30 times 5. All right. Anybody do it differently? Yeah. Okay. All right. Okay. All right, yeah. So that's the spirit of it, right? We know every second it's going up 30. So then in this next, we don't want to go a full second, but 0.7 of a second. And did everyone figure out how much does the speed increase in 0.7 of a second? Yeah. 21. Okay, so then we get 171. So what are we really doing here? And doing that process that they just talked through there, what do we really, so what we said, 171? What, that little calculation that you just did, how does that relate to things we've been doing in this course? Okay, how does it relate to things we've been doing in the course? That little question that I asked you in the, yeah. Okay, but how does it relate to things we're doing in the course? Yes, sir. Okay, yeah, I guess you could say that. I'm looking for a magic word here. Okay, so instead of you trying to guess what I want you to say, aren't we accumulating changes in velocity? We're accumulating changes in velocity, right? Velocity, the changes are accumulating. velocity doesn't accumulate, but you can think about changes in velocity accumulating, right? Okay. And how are they accumulating? The changes in velocity are accumulating by 30 meters per second each second, right? Each second. Is that right? Changes in velocity are accumulating by 30 meters per second each second. Okay. And so, and lots of you have already picked up on this, and you've been saying it, that we're talking about acceleration. Okay, that's the same thing. The acceleration of the shuttle is 30 meters per second per second. 30 meters per second per second. Meaning every second, the velocity increases by 30 meters per second. Accumulating changes in velocity. 30 meters per second each second. Okay, so I want you to sketch a graph of the acceleration function for the rocket. So feet per second on the vertical axis, seconds on the horizontal axis. What would the acceleration function look like? Acceleration function. Did I? Okay, meter. Okay, sorry. So it's meters. Sorry. Yeah, meters. It's not a units problem. All right, where is Grady cool? Where's Grady? Grady, tell me. What do you? All lines are straight. Straight across. Horizontal line. Okay. All right, so that, as time goes by, what's the acceleration? It's just 30, right? It's 30 meters per second every second. Okay, so now I want you to write a function for the net accumulation of change in velocity of the shuttle since time equals 0. So I want to write a function for the net accumulation of changes in velocity. What kind of function is that? It's the net accumulation of changes in velocity, then it's what quantity? Oh, it got you there. Where's Daniel Wallace? Daniel? So if it's a function for the net accumulation of change in velocity, what kind of function is that? What's the quantity? Is that acceleration? We're accumulating changes in velocity. It's velocity, right? It's velocity. All right, so that would be writing a velocity function. So where's John Maelstrom? John here? How about Seth Hallhouse? Seth, did you get a function? Is it okay if I make our independent variable t? So I call it a t. So it'd be 0 to t of, what was it? Need something else now then. Anything. Switch them, a of x dx, that's fine. Okay, and so, but some of you already know what that function is, right? What is that function? When I asked, so who did I ask? What the at 50, what was it? 5.7 seconds with the who did I ask? Yeah, and how did you get it? What did you do? He just took 30 times the number of seconds, right? So we know what that function is. That function is 30t. Okay, so this is the difference, if you remember from Calc 1, if you were with us in Calc 1. This is the difference of representing a function in, this is called what we call open form. Open form reflects the process, this accumulation of changes, right? reflects the process, accumulation of changes, but it's not readily computable. We always have to put these in GC and let the computer do it, right? And go through its making intervals really small and actually accumulating tiny bits. We don't want to do that. We want to let the computer do that for us. This then is called a closed form. Very easy to compute values of velocity, right? Because all you do is multiply 30 times whatever time you're talking about. So coming up in a week or so, we're going to talk about we want to for our open form functions, we want to have closed forms. We want to have closed forms because those are a lot handier, convenient to work with, and they just spit out values of the dependent variable very easily for us. We don't need technology. If it's a simple function, we won't need technology to get values of the dependent variable. And even sometimes with technology, getting values can take a long time, depending on how complicated this is. So that's why we like closed form. So again, this is an example. Integral function is an example of open form. And your standard functions, sine, cosine, exponential, polynomials, are examples of closed form. So all these accumulation functions that we've been writing them in open form, in integral notation, reflecting the process of accumulating changes, right? But there's a great advantage to closed form, and so that's going to be kind of the next, after we get through 8.5, the science section, that's what we're going to be talking about in chapter 9. Developing closed form for lots of different kind of open form integral functions. Okay, but I digress. All right, so we're talking about acceleration. So what does this imply about acceleration and velocity then? What does this open form expression, if we look, we got the acceleration right there. What does that imply about acceleration? Because we're experts at these net accumulation functions. Yes, sir? Is that what you're going to say too? Right, so exactly, and it's rate of change, right? It's how fast the velocity is changing per second. And so and because it's there in our net accumulation function as the function, it's rate of change of velocity. Okay. So on the moon, the acceleration of falling objects is 5.4 feet per second per second. So what does this mean? And make a table showing the velocity of an object falling toward the moon every second for 5 seconds. You can think and work on it by yourself, or you can work together. All right? So first of all, what does it mean that the acceleration of falling objects on the moon is 5.4 feet per second? And then make a table showing those velocities every second for 5 seconds. Go. So what does it mean that acceleration is 5.4 feet per second per second? Okay, so it's the rate of change of velocity. Okay, but just what does that number mean, right? So it's the rate of change of velocity, yeah, but what does the 5.4 mean? What are we talking about when we say the 5.4? Yeah, right, yeah, so every second, the velocity changes by 5.4 feet per second, and then that description then, but actually more than that. So if it's a rate of change, then really we know a lot more than that it goes up 5.4 every second. What do we know? Yeah. Okay. For any change in time. Yeah, good. So, yep. So now for any change in seconds, not just 1 second, but for any change in seconds, what the change in velocity is 5.4 times that change in seconds. If it's that's our broadest meaning, our fullest meaning for rate of change. It tells us a lot more than what's happening every second, but in any change of time. So in 10 seconds, what's the change in velocity? 54 feet per second. In a tenth of a second, what's our change in velocity? 0.54, right? Okay, so that's our fullest meaning for the rate of change. Okay, and then knowing that, this table is easy, right? At 0, we have 0, 1, 1.8. What is it? Okay, and then what about at 4.1? What would you do? At 4.1, to get 4.1, you would do 21.6 plus a tenth, right? So that's our dV equals 5.4 dt. 22.14 feet per second. Okay, another example. So this is the acceleration of a car. So this is in feet per second per second. Okay, so let's just look in the first 2 seconds. I'll zoom in on that. That's good. So in the first, say, 2 seconds, can we make a same thing? I want to know the velocity of this car. So this is like a toy car speeding up here. Or I'm sorry, this is the acceleration, right? This is not speeding up. This is the acceleration in feet per second versus seconds. So I want to do the same thing we just did. And I want to get the speed of the car, and let's go with every half a second for the first 2 seconds. 0, 0.5, 1, 2 seconds. What's the speed at each of these times? So same question as before. I'm giving you, all right, here's an acceleration graph, and I want to know the speed at these different points in time. So why don't we work with someone else for this? So either group of 3, 2, discuss, see what you come up with. Okay. So like if we wanted to get the speed at 0.5 seconds, given this acceleration profile, what is it? Did anyone come up with the speed at 0.5 seconds? Vivian. Okay. And why do you need to do that? Okay. So what's different here? Good. So yeah. So in order to make any progress at this, we need to have constant acceleration. That was the previous examples were easy because it was always the shuttle and the falling object. Constant acceleration. So calculating changes in speed were really easy. We could use dV equals a dt, right? We could just use that constant acceleration. But now the acceleration is totally changing. So you said take that first interval, Vivian said, and do what? Okay, so you just said let's call it 0.08. So right about here like this. So now that we have a constant acceleration, then we can actually say, and I should have told you this is a car starting from rest. Okay, starting from rest. All right. So then if we estimated that to be 0.08 feet per second for the whole interval, for that whole 0.5 seconds, then what is our estimated speed or velocity at 0.5 seconds? Yeah, it'd be 0.08, the rate of change times that change in time. So it'd be 0.04. Okay, and then did anyone else do something like this? Okay, and so what did you have for the second interval? What did you?
The next interval I considered it to have about a constant rate of change of 0.25 feet per second.
0.25. That's up here, like this.
Yeah, right there.
Something like that. And so how are we going to get the speed then at the end of 1 second? Go ahead.
Then I would take that 0.25 multiplied by half a second.
Right.
Give me a change of 0.125 and add it to our previous velocity.
Nice.
0.04.
Right, because this is all, getting speed from acceleration is all about accumulating changes in speed, right? So we're accumulating. We're going to take what we had from before and add the new but no, you said 0.25, right?
Yeah, I was saying 125 would be multiplied by a half, but you're writing out the times a half, which is the same thing.
Oh, okay. And that gives what did you get for that total value?
Well, with that one, it would be 0.129
feet per second. Something else? It's something else? 165. The total is 165? Okay, thank you. Okay, etc. So this should feel very familiar. Now we've got a changing rate, right? A changing rate. So in order to accumulate changes in the quantity, we're going to have to assume constant rates. In this case, constant accelerations over intervals, and then we can use constant rate of change to accumulate changes in speed or changes in velocity. Okay? So we could continue like that. Does that make sense? Anyone? Any questions on that? Yeah. Yes. Right. Yes. So, right. If the rate of change, if we think of the rate of change as area, then the rate of change is acceleration. Sorry, acceleration is our rate of change. Then the signed area, the rate of change for signed area would be the function value, right? So that would be yes. What you're saying is true. Because the function value is acceleration, and if you do signed area, you want to accumulate signed area. You're going to use the function value, which is acceleration, which is then going to also give you net change in speed, or net change in velocity. Other questions? Okay, so I actually have two cars. No, we're done estimating, okay? We're done with estimating. Okay, so we got two cars, and I'll tell you the blue one is car 1, and the red one is car 2. And I got some questions for you. So at 2.5 seconds, so we were working on car 2 just now. We were working on kind of accumulating changes in speed to track the velocity of that car 2 over those first 2 seconds. So now at 2.5 seconds, which car is moving faster? At 2.5 seconds, which car is moving faster? Can you see red and blue? Does it come up, the difference between red and blue? I took the graph off of that. I have an idea. Wow. The color just doesn't come through. It's worse. All right, so I'm doing my best to show you red and blue. Okay, so car 2 is red, car 1 is blue. Which car is moving faster at 2.5 seconds and why? Discuss. Go. So the question is, which car is moving faster at 2.5? Jonesy, you're up. So what did you guys talk about? Car 1. But the car 2 graph is higher. Okay. All right, so you looked at signed area. So can we talk? Yeah, so that's okay. Can we talk about it in a way that doesn't say talk about signed area? Yes, sir. Okay. And so how do you know that? Right. So considering what we just did from 0 to 2, that we did car 2, what did we do? We took constant rates, right? We took constant rates and we accumulated those changes. So when we do that with car 1, what's going to happen? We're going to start assuming constant accelerations and accumulate changes in speed. And how is that going to compare to car 2? Much greater, right? Because our constant accelerations, if we thought about little constant accelerations, would be much greater. And so car 1 is clearly accumulating a lot more changes in speed than car 2 is. Now, what happens from 2 to 2.5? Well, now car 2 is gaining speed more than car 1, but not nearly enough to overtake what happened in the first 2 seconds, right? What happened in the first 2 seconds is car 1 gained a lot more speed than car 2. Now car 2, is gaining speed more than car 1 in this little, from 2 to 2.5 seconds, but again, not nearly enough to undo what was done in the first 2 seconds, right? So next question is, when will the cars have the same speed for the first time? When will the cars have the same speed? So right now at 2.5 seconds, you all agree that car 1 has a higher velocity. Agree? So when, or maybe they won't, but do you think that car 2's speed, or car 2's velocity will ever reach the velocity of car 1? And if so, when do you think? Yeah, talk. Go ahead. Talk it out. Nick, you're up.
Oh wait, no, didn't you think that it would be somewhere in that last section where car one starts to dip down and car two is still going up, that car two will make ground on car one?
All right, so you're saying somewhere between like 5 and 7 seconds. This is 5 here and 7 here. They say between 5 and 7. What do you think? Okay, so agreement. Now I want to answer this question definitively. I know exactly what time. How can I answer this question definitively and know exactly what time they're going to have the same velocity at the first time they'll have the same velocity? I want to answer this definitively. How can I do it? Is that an and?
Yeah, technically.
Okay.
Basically, well, we were talking about this as assigned area, but if you were to take the integral of the acceleration function for car one,
Okay.
and the integral of the acceleration for car two,
And what would those give you?
what's that? Those would give you the the assigned area. Well, that would give you the accumulated velocity.
Okay, which is?
And you want them equal to each other.
Okay. So we talk about integral of acceleration function. What kind of quantity, what function will that give? That's the velocity function. So if we actually had the true velocity functions, we could do it. So here they are. So they're A1 and A2. So I've defined those in GC. So write out command lines in your notes. What command lines would you write out that I'm going to type in so we can answer this question? When will they have the same velocity? When's the first time they'll have the same velocity? So what do you think I should type that's going to help me answer that question? Miranda, any idea? What do you think? You're up. No? So what do we need to answer this question? We want to know when they have the same velocity, the first time they have the same velocity. So we need how about Jordan Evans? Where's Jordan? Yes, sir. Okay, do we know how to do a function? Yeah, so what should we call it? What kind of function will it be? So let's do, yeah, v, right? So we'll do v1 t equals so I'm using my independent, I'm going to use t, 0 to t of a1. Type out that whole rule again? You can, but it's a waste, right? We beautifully defined this function. Let's use function notation to our advantage, right? So just a1. You just want to use x now, okay? And then let's do it for the other one. Okay. So is that helpful? So now we want to answer this question. How should we answer this question? What should we do? Somebody new. Yeah. Okay. Yeah, so let's do that visually. So I think the graph is really helpful for that. So how can I do that? I want to set them equal. So I want to do that visually. What should I do? Tell me your name. Yeah. Jessica. I want to figure out when those velocities are the same, and I want to do it using a graph, visual manner. So what should I do? But instead of just isolating that one moment in time, let's just graph them. Let's just graph them, right? So what would I tell me? Yeah. Sorry. Y is equal to, and I'm going to use in a new window. So y equal to v1 of, what am I going to do? T? X, right? If I'm graphing, this is telling GC to put it on the x-axis. And then this is from 0 to 8. Not 9. That won't show much, right? And that's not much. Okay, and then we'll do the other one too. Oops. Let's do purple and green. Do they show up? Oh, good. They show up nice. All right, purple and green. So which is which car? Which car is purple? We know that's car 1, right? It accumulates much higher changes in speed at the beginning, so it's going a lot faster at the beginning. But then, after about 5 seconds, car 2 is catching back up in speed, right? Catching back up in speed. So, what do we look for? It should lock. It's not locking. All right. So how did Nick do here? There it is, right there. It's right there. 5.6 seconds. So 5.6 seconds is what they said. Somewhere between 5 and 7. 5.6 seconds is where. Explain exactly what's happening with the cars at 5.6 seconds. So take a second to talk. Exactly what's happening at 5.6 seconds with those two cars. Go.
Yeah.
Okay, so at 5.6 seconds, what is happening? Where's Jessica? George? Jessica again. Velocities are the same. Okay, so at 6 seconds, which car is ahead? Which car is ahead at 6 seconds? Further down the track. Car 1 or car 2? So this is. Okay, they started at the same place. All right, so tell me, which car is ahead? What's your name? No.
We have to do the net accumulation of that function.
Okay, can we guess? Can we make a guess here? Can we make a good guess at which car has traveled further at 6 seconds? Car 1? Okay. Because what? Distance traveled or position now is The accumulation of changes in velocity. So even though now car 2 is going faster, what happened in the first 5.6 seconds? Car 1 was going faster that whole time. So at 6 seconds, we bet a lot of money, in fact, our whole life savings, that car 1 is still ahead. Okay? Even though now car 2's speed has surpassed, or velocity has surpassed car 1. So I want to know, when are they in the same place? When does car 2 pass car 1 for the first time? I want to know that. Answer that question. How can I answer that question? Oops. All right, so I need position functions now, right? So position function for car 1 will be, I'll call it S, will be what? 0 to t, v1, and then for 2, S sub 2 of v2. So then what is the relationship of position S to acceleration? Say I wanted to write the position function in terms of acceleration. What would that function look like? Yeah, so it would be an integral of an integral, right? It's like a double, it's called a double integral, right? It's an integral of an integral. Let's go back and graph this on this axis over here. So we're going to graph So I'm going to graph the S1 function and the S2 function. So we'll go back to blue and red. So blue for car 1, red for car 2. We'll turn off the acceleration. So now we're back on the left side. What do you think? Will car 2 catch car 1? Maybe. Oh. And then, why is it taking so long? Right, it's doing, this is the idea of open form calculation. Open form calculation, calculating an integral, means calculating all the bits, but then it's doing for every bit in the first integral, it's got to do the whole set of bits on the other one, and then it goes to the next bit. It doesn't have the whole set of bits on the next one. So this is car number 1. All right, is car 2 going to catch car 1? Or not?
$20.
Oh, it has to start over.
We're at the horse track
If you want to wait and see, you can wait and see. Have a good weekend. Hi. Sure. Sure. Just, yeah. We're just gonna, let's just wait until this finishes. Yes? Maybe?
Tie?
My computer didn't have the memory to actually calculate those curves.